Good afternoon, everyone. Welcome to the research track. My name is Manish. I'll be moderating the session. In this session, we have 5 speakers. 4 of them are actually from Georgia Tech, so it's a very large representation from Georgia Tech. The flights must have been on sale, apparently. And we have Nitin from Cornell, who will be presenting. From Georgia Tech, we have Robert Lychov, Maria Conte, Sean Donovan, and Hyojo Kim. They'll be talking about some of the work they've been doing as part of their PhD thesis work. And some have graduated, some are close to graduation. So if you are interested in recruiting, please approach them after the session, not during the session. And we'll get started. Robert, you'll be up first. Robert will be talking about some of the work he's done in looking into BGP security and how things work when you have partial deployments and whether it's worth the effort.
All right. Good evening, everyone. Thank you, Manish. So this is joint work with Sharon Goldberg from Boston University and Michael Shapiro from Hebrew University. And majority of this work I actually did when I was a visiting student at Boston University. So let me just spend a couple of slides giving a very high-level idea of what this talk is about. So as we all know, many widely used networking protocols of today on the internet were not actually initially designed with security considerations in mind, and this is because they were intended for parties that trust each other. Should I speak louder? Okay. Here we go. But of course, this is not an assumption that's true, and it has been true for a while. But what we also know is that deployment of new protocols on the internet is actually very tricky. It takes time. It's very complex. The internet is very large, constantly growing. And we've seen this with DNS and DNSSEC, as well as IPv6 and IPv4. These protocols have been for a while in partial deployment, and maybe for a while more. So specifically, this talk about BGP routing on the internet. We know that BGP suffers from various security vulnerabilities, and we cannot expect that any security solution can be deployed overnight. So there's now a big push by the ATF to standardize secure protocols, specifically BGPSEC. And the focus of this study is to understand the benefits and potential vulnerabilities when BGPSEC is only partially deployed. So let me give you a very quick overview of how we did our study and what are our results. So this is a partial landscape of BGP defenses. The x-axis here represents the security provided by a particular protocol. On the very left, we have BGP that provides no security guarantees. We then have RPKI, which provides origin authentication. It is being currently deployed, and it allows for its cryptographic operations to be done offline. Which is certainly very nice. On the very right, we have BGPSEC, which is currently being standardized by the IETF. It provides protection from many more sophisticated attacks potentially than RPKI, but it requires its cryptographic operations to be done online. And we're specifically interested in this section of landscape where BGP and BGPSEC have to coexist in partial deployment. Just a note here, BGPSEC is being standardized to run on top of RPKI. And we're interested to know, what does partially or fully deployed BGPSEC offer over RPKI? So what benefits we get from BGPSEC, and are the benefits worth the efforts to deploy it? In other words, is the juice worth the squeeze? And so what we find is that, in fact, the road to BGPSEC full deployment can be very tricky because introducing BGPSEC partially to the internet can sometimes introduce new, unexpected scenarios and vulnerabilities. Not fully deployed BGPSEC, we find, provides very meager benefits if network operators do not prioritize security above all other considerations in their routing policies. All right, so let me give you just a quick overview of the background for this talk. As we know, BGP is just a distributed protocol where ASes exchange information about reachability information about various prefixes. So this is a toy network that I've taken from about 2 years ago from UCLA S-level topology. So the origin announces itself, as we know, and its neighbor selects the direct route and then propagates this announcement by preparing itself in the route. So on and so forth. This process continues until everybody learns of a route to the origin. But notice that there's no way to check for authenticity of these announcements. So a particular attack that we focus on in our study, we call the one-hop hijack attack, is where an attacker simply pretends to have a direct edge to the origin and announces a one-hop route that it actually doesn't have. So in this particular case, which route should Sprint choose? Well, if it uses a simple routing policy here of just preferring a shorter route to the longer route, it will fall victim to the attack. And as you can see, this could probably be very disruptive because Sprint may have many customers who would want to reach the origin through Sprint. So here's where BGPSEC can come in and prevent these kinds of attacks. So first of all, it requires RPKI to be deployed. RPKI provide public secret key pairs for every AS. And with their private keys, AS can sign their announcements in such a way that the recipient of every announcement will be included in the announcement, in the signature, excuse me. So, and also the signature of every AS will be included in the propagated announcement. This way, every AS can then check the signature of every AS with their appropriate corresponding public keys. And so when the attacker tries to pretend that it has a direct edge, although it can sign on its own behalf, it cannot sign on behalf of the origin, and this is something that Sprint can check, reject the bogus announcement. And so this is how BGPSEC more or less on a high level works. So in this talk, we are going to suppose that RPKI is fully deployed. We understand that RPKI will prevent prefix hijack attacks, so we do not focus on these kinds of attacks, and we specifically focus on one-hop hijack attacks. And we're interested in understanding what happens when BGP and BGPSEC have to be in coexistent in partial deployment. So let me give you some understanding of why this is not trivial. So suppose there are two ASes that do not deploy BGPSEC. Here they are marked in white. And according to the BGPSEC standard, all of the ASes that do deploy BGPSEC have to still use legacy insecure BGP when they exchange routing information with those ASes that do not deploy BGPSEC. And this is, of course, done for backwards compatibility so that some ASes that do not deploy BGPSEC do not get disconnected, such as, for example, Siemens and A in this case. However, what happens when one of them turns rogue and then runs an attack? The question is, should Sprint choose the long secure route on the left or the short insecure route on the right? Of course, it cannot know in advance that this is an attacked route. So this is not at all trivial, and there may be many different ways that Sprint can try to make up this decision. So let's explore this point a little further. So this is just a BGP decision process that a router would go through to select a route from multiple routes. First, it would consider local preference, then route length, preferring shorter routes over longer routes, then potentially a multitude of other considerations that we'd not consider in our study, such as multiple exit discriminator and stuff like that. And finally, if that's not enough, it would break ties in some potentially arbitrary but consistent manner. And we also in our study assume that a local preference decision are based on business relationships with neighbors. So the question is, in this decision process, where should security go? Well, in an ideal world, it would be prioritized above everything else, and that would be sort of the security first routing model. However, network operators may think that local preference and route length is more important, in which case security could be second or third. And in fact, it turns out that according to a survey from about 2 years ago, that there's no consensus among network operators how security should be prioritized. And of course, the most idealistic security first model got the least support, while the most probably least intrusive security third model got the most support, and security second somewhere in between. And we study all three of these models. In our studies, to understand routing outcomes, we use a concrete local preference model where customer routes are preferred over peer routes, which are preferred over provider routes. But also, as I will mention toward the end of the talk, all of our results are robust with respect to various local preference models, which are variants of this preference model. So now let me give you an idea of what kind of interesting and unexpected scenarios we have encountered in our studies. The first one is called the protocol downgrade attacks. Imagine a security third scenario where security, basically route length is more important than security, right? So again, an attacker runs its attack. It's a one-hop hijack attack, and Sprint has to make a decision which route to select. Now, because this security third, here route length is more important than security, and so Sprint could actually fall victim to this attack, even though originally it had a secure route. So this is what we call a protocol downgrade attack, because before the attack, Sprint had a secure route that it learned with BGPSEC, but during the attack, it actually has decided to switch to an insecure route and that is attacked, that it has learned with BGP, and that's just because of its own policy. However, of course, there could be many other ASes behind Sprint who also run BGPSEC, customers of Sprint, who would then also be sort of victims of this attack because of Sprint's decision. We can show that although these things do happen, protocol downgrades when security is third or second, they do not happen when security is first. The second, probably the most counterintuitive scenario that we have encountered, which we call collateral damages, happens when security is second or first. So this is an example of security second. This more complicated toll network was also taken from UCLA AS level topology from about 2 years ago. We will focus on the origin AS on the bottom left, the attacker on the bottom right, and a few ASes in the middle. Let's consider the situation before AS X deploys BGPSEC. We have all the secure ASes selecting the secure route, because security is second and security is more important than route length. All the ASes on the top right fall victim to the attack, and there's no way they can detect this because they don't deploy BGPSEC. Z just selects the direct route, and X, well, X learns of all the routes from Z and V via BGP, because it does not deploy BGPSEC. So it just selects the shorter route and then propagates it to Y, who then selects the route through X. So what we have here is 5 secure ASes and 8 happy ASes. These are ASes that avoid the attacker and select legitimate routes. Now, watch what happens when X deploys BGPSEC. Now it learns of routes from V via BGPSEC, and because it cares about security, and because security is more important than route length, in this particular scenario, it would actually switch from a shorter insecure route to a longer secure route. And what does this mean for Y? Well, now, because Y doesn't care about security, because it doesn't deploy BGPSEC, it thinks that the route through W is shorter, and so it would just select that. But actually, this is the attacked route, right? And so we say Y experienced collateral damages just because X deployed BGPSEC. So the crazy thing is that we've increased the number of secure ASes from 5 to 6, but we've actually decreased the number of happy ASes that avoid the attacker and use legitimate routes from 8 to 7. And what we can show is that although this can happen when security is prioritized first or second, it does not happen when security is prioritized third. So the third interesting scenario that we have encountered in our study is called routing anomalies. For the sake of time, I won't go into the detail, but basically what we found out is that routing policies can sometimes interact in ways that cause BGP wedges and routing oscillations, or instabilities, they're called, when ASes do not prioritize security in the same way. And this, of course, can be very disruptive, because sometimes what happens is the network would end up in undesirable routing outcomes. But what we can show is that these things do not happen when all ASes prioritize security the same way, and this is what we assume in our study. Okay, so now let me go over the final part of our talk, and then I will summarize, where we'll tell you about how we actually quantified benefits of partial BGPSEC deployments. So first, how do you actually quantify BGPSEC benefits? So let us consider, for example, this network again. Let us fix an attacker, an origin, and the set S of ASes that actually deploy BGPSEC. Here, this set is empty because no one deploys BGPSEC. And let us denote the ASes that select legitimate routes and avoid the attacker as the set of happy ASes. So in this case, this set is 3, while in, for example, this case, when everybody deploys BGPSEC, the set of happy ASes is actually 5. Okay, and what we're interested in, and this is what we use as our metric, is the average of all these happy ASes, where the average is taken over all sources, all destinations or origins, and all attackers. And it is with respect to this metric that I'm going to present to you our empirical results in the next 2 slides, and then I will tell you how we obtained these results. So this plot, bar chart, shows BGPSEC benefits bounds of RPKI. These are lower and upper bounds that are irrespective of who actually deploys BGPSEC on the internet. The horizontal line presents a lower bound when RPKI is deployed and prefix hijacks do not happen. This means that even when no one deploys BGPSEC on the internet, in our empirical results, show that the average fraction of ASes that avoid the attacker is 53%. The average actually here was taken over all non-stub attackers. We assume that stub attackers can be prevented in other ways than BGPSEC. The height of each bar represents the upper bound with BGPSEC for every secure routing model. That is, as deployment of BGPSEC becomes really, really, really high, this is the maximum benefit that you can get on average. And what we show is that in the security third model, which is sort of the one that got the most support from network operators, at most we can get is 17% extra happy ASes. These are ASes that avoid the attacker, which is actually quite small if you think about it. So even when your BGPSEC deployment approaches 100%, you're really only having 17% improvement maximum on average. Security second is a little better, and security first is, of course, great because this is where you can get all the benefits that you can, pretty much. So the next thing that we try to do is try to see how close we can get to these upper bounds with various deployment scenarios. I'm going to show you the biggest deployment scenario that we have experimented with that consists about 56% of ASes on the AS level topology that we used. We've taken 13 tier 1 ASes and then the next 200 top ASes with respect to customer degree, and then all of their stubs. And what we've seen is that although you can get about 25% improvement when security is first, which is pretty good, actually when security is third and second, you only have 5 or 10% respectively, which is actually quite meager and somewhat disappointing. So let me just give you quickly summarize how we obtain these results and then summarize. So as I said, we've taken a UCLAS level topology from about 2 years ago, and then we use large-scale simulations to determine routing outcomes and find out upper and lower bounds, as well as the security benefits for many different BGPSEC deployment scenarios that we did. To gain some confidence, we also ran all of our experiments over another topology that was augmented with over 500,000 of peering edges that we've inferred from IXP data also about 2 years ago. And note that this is like 3 times as many links as in the original graph. We've also accounted for traffic patterns by focusing on only certain destinations, such as content providers, as well as attackers. And finally, we tested all of our results against different local preference models, where, for example, shorter peer routes could be preferred over longer customer routes. And these kinds of local preferences are more appropriate for ASes such as content providers. So to summarize, again, this is the landscape of partial BGP defenses. We focus specifically on this section where BGP and BGPSEC have to coexist. We found that it was somewhat tricky because you can get these strange scenarios such as protocol downgrades, collateral damages, and routing anomalies. It turns out we found out that protocol downgrades actually play a major role in all of our results, empirical results. And the final message that I think is to take away is that unless security is first, or BGPSEC deployment is very large, and by very large I mean potentially over 60%, security benefits from partially deployed BGPSEC we find are somewhat disappointingly meager. Another way of saying it is this kind of no free lunch. Either network operators would have to prioritize security above all other considerations, or we may have to potentially wait for a very long time before we actually see any real BGPSEC deployment benefits. So thank you for your attention. Please check out the full version and email me if you have any questions.
We have time for a couple of questions.
This room has too many pillars. Michael Sinatra, ESNet. This is going to sound a little harsh, and I don't have any way of sugarcoating it. But you're academic, so you are used to it. I'm trying to grapple with the so what factor here. what you're basically saying is that we can't realize benefits of BGPSEC and if it's only partially deployed. Okay? What you're also saying is that you sometimes get into trouble when you have BGP routing policies that cause you to get into trouble. Sure. We know that, for example, if you didn't have web browsers that could do SSL deployed universally, that SSL wouldn't be very useful. I still believe that DNSSEC isn't very useful until everyone does validation. And no, not everyone's, we're doing 8% of validation. There's no incentive for Bank of America to sign their zone when there's 8% of us doing validation out there. So, you know, IPv6 is pretty much the only thing where you can do partial deployment until somebody really important has IPv6 only, and then partial deployment for that doesn't really work very well either. So it doesn't really seem like, you know, there's much that I can take home and say, okay, what can we do differently? Because it just seems to make sense that this is, yeah, if we do partial deployment of BGPSEC, that's gonna be what happens. Your assumption that the starting point of your model, which is that everyone does RPKI, but not everyone does BGPSEC, I also think is questionable because not right now, hardly anyone does RPKI. So I'm not really sure. And we've seen as Wes's presentation that there's significant impediments to that. So there's probably not a question. I guess I could put a question mark on the end of all this and make that into a question, but it's mostly
Robert,
just a rambling comment.
You must have come across some of this criticism during other presentations.
I think you can say about a lot of work that it seems kind of obvious after you've done it. This is, like you said, academic works. It's about awareness. It's about letting people understand what the problems are and potentially start thinking about how to deal with them. Now, in terms of the RPKI assumption, I agree, that's potentially a strong assumption, but this is just something that we had to do in our studies because if we didn't assume that RPKI is fully deployed, it would be sort of even more of a mess to study. But that's an interesting sort of, you know, next follow-up is to see, well, what happens when RPKI is only partially deployed? Potentially, you'll see even, you know, fewer benefits, and then it would be obvious. But at this point, we don't know.
And I guess there is some value in being able to quantify just how much, which you've done a study on. Last question.
Rüdiger Volk. Well, okay, essentially commenting, yes, the result is not really surprising if people do not put security in high priority. Well, okay, what are you expecting? The work quite certainly has some value by helping people understand that if they are going to do something about security and effectively in their policies do not care, we can see how bad the result is. So I think it's probably good data for people who are deciding how to evolve their policies. And, well, okay, I also think for the collateral damages there are, I could imagine a market situation where my customers, my multi-home customers, might actually put into their policies preferences towards the secure upstream versus the known, not secure upstreams. So things actually could change something. But yeah, of course, the providers that are not doing the security thing in the path may actually lose traffic if people prefer secure.
Yes, actually, this goes back to Sharon Goldberg's previous paper, which got some criticism. But yeah, I mean, certainly there's some potential for future analysis of policies and how they can involve different contractual obligations, things like that. Thank you.
Thank you, Robert. Next up will be Maria, also from Georgia Tech. She will be talking about some of the work she has done on AS reputation. We're going to try to keep the talks to 15 minutes and so that we have time for questions, because clearly the questions are very valuable.
Hi, my name is Maria Conte. I will talk about AES Watch. This is joint work with Professor Roberto Perdischi from University of Georgia and Nick Fimster from Georgia Tech. So AES Watch is an AES reputation system to expose bulletproof hosting AESs. Every year, hundreds of new AESs are registered. Some of them are completely dedicated to criminal activity. They are fully controlled and operated by cyber criminals. They provide the perfect safe environment for them to operate. Some of those bad AESs are still around. Think, for example, the notorious Russian business network or Encoding. Many of them have already been shut down, and others have not been recognized. So, for example, think of well-known cases like Macolo, Atrivo, Intergage, and V-Line, which were shut down. The community's response to defend against the bulletproof hosting AESs was to develop AES reputation systems. The way that these reputation systems work, for example, BGP racking, host exploit, fire, is that they rely on direct observations of cyber criminal activity that originates from these bad AESs to assign a reputation score. So, for example, if they observe an AES to send large volumes of spam over a large amount of time, and this badness, this concentration of badness persists for long enough, then they assign a low reputation score. Unfortunately, it turns out that delivering AES reputation, monitoring the data plane behavior, or if you will, that this badness that originates from its AES, is not an easy task. For example, the most recent report by Host Exploit, which was on March 2014, reported a number of AESs. Some of them are obviously not controlled by cyber criminals. They are just badly abused. And some of them, they are indeed bad. So then the decision goes back to us, the user, the network operator, to decide which ones of them are truly bad and they should do something about it, or which ones are just badly abused. What we do need is an AES reputation system that is actionable. Think, for example, the case where we want to decide to assess the risk before making a peering decision. What would be the collateral damage if we peer with an AES that has a truly bad reputation? Or if we want to prioritize the traffic that originates from bad AESs? Or if we want to inform the community that an AES, that a truly bad AES is out there and people should do something about it or they should know about it. Instead, we're taking a different approach and we're looking at the control plane behavior rather than the data plane behavior. We started by examining the behavior of confirmed cases of bad AESs that were observed by the community, confirmed cases that were reported in blogs. And we found out that they do share some common behavior on how they are changing their connectivity. So, for example, in this case, we tracked AS Troyak that was reported back in 2010, and we studied how it changed its upstream connectivity and downstream connectivity. AS Troyak started by connecting with 3 legit upstream providers and 5 bad customers. And before going offline, it switched to forming a peering relationship with another bad AES, so it relied on that for upstream connectivity. It dropped 3 of its bad customers. And it turns out that AS Troyak was not the only one. Most of these AESs, do not act in isolation, but they form an infrastructure. So, for example, the bad AESs that are at the bottom usually rely on some other AES for upstream connectivity, and they prefer to not directly connect with legitimate AESs. I will present AES Watch, the infrastructure of the architecture of the system that is doing exactly that. It monitors how those AS is changing their connectivity, and also how they advertise their prefixes. AS Watch has two phases. It operates in two phases. First, we have the training phase and then the operational phase. At the training phase, we start with a set of legitimate ASes and a set of confirmed cases of bad ASes. We monitor how they are changing their connectivity and how they are advertising their prefixes. Then we feed these statistical features into a classifier, and we get a trained statistical model. Then in the operational phase, once we have this trained model, we can feed AS Watch with a list of ASs we want to test, and we want to assess their reputation. Again, following the same procedure, we compute the statistical features, and comparing them against the model, we get an AS reputation score. You can think of this reputation score as simply a number from 0 to 1. If it goes close to 0, then the AS that we tested is legitimate. If it goes closer to 1, is bad. Now we'll talk about what are those features, like in this box over here, what are these features that the AS Watch is looking at? In other words, how does it fingerprint the behavior of an AS on the control plane? So the first set of features that it captures is the connectivity changes. It captures how an AS is changing the upstream providers, the customers that it links with, and so on. How aggressively it's doing that in a short amount of time, if it links with other suspicious ASes, and so on. Second, AS Watch captures the routing dynamics. We are looking at, for example, short-lived announcements. And the reason that we are doing this is because that set of confirmed cases of bad ASs that we monitored, they are shown to, for example, advertise a prefix for a short period of time, then send large volumes of spam, and then withdraw that prefix. And third, AS Watch captures how those bad ASs are rotating their prefixes. Some of them, for example, may advertise a set of prefixes for a day, and then in another period of time switch to a totally different set of prefixes. And the reason that they're doing that, it seems that it is simply because they want to avoid blacklisting. We evaluated AS Watch on confirmed cases of bad ASs, which we collected from blogs. When an AS was either taken down by law enforcement or when the community was aware that something bad is happening, some of those cases that were reported in blogs. And after testing AS Watch, it reported a high accuracy in true positive. We were able to detect over 93% of those bad cases of ASs with a false positive close to 5%. We would like your help evaluating AS Watch. We would like to know more about how you decide to peer with an AS, if security and the AS reputation plays any role in that. We would like to know if you have ever had to deal with suspicious AS, in the sense of depeering, or if you had to consistently prioritize their traffic. We would like to know how could AS reputation potentially help your work. So please come and talk with us. Thank you.
Thank you, Maria. Questions?
Hi, Doug Montgomery. So did you say you're focusing strictly on the control plane? How do you train? Like, you seem to be training on ASs that emit a bunch of spam, but that seems like the data plane to me.
No, actually that was just a motivating example to show why we're looking at this specific set of features. So our ground truth was ASs that were reported by the community in blogs. So we took those set of ASes and we tracked them over a period of time. So from there, we didn't look at the data plane at all. We said, okay, this is our ground truth. We're looking at how these ASes change their providers, their customers, and so on.
So you're looking at...
And also how they advertise their prefixes, like if they were short-lived and things like that.
So you're looking at BGP announcements?
Yes, the AS graph and the BGP announcements, yes.
And so did you learn anything from the false positives? Is there some sets of behaviors that will always fool such a system, or is it something that you can improve and train around?
That's a good question. So this is where we would like your help, because those reports in blogs, they only told us an approximate period of time that the AS was bad, and also didn't tell us anything about which prefixes were actually involved. So AS Watch did very well considering this loose ground truth that we had in our hands. If we are provided with a better ground truth and better period, like a more precise period when those ASs were bad, we can evaluate the AS Watch and report much better.
I assume somewhere in a publication or your thesis
there is
a discussion of the false positives, right? Because in all these spaces, the danger of the false positive is often thought to be a bigger threat than mitigating the problem, right?
Right. So AS Watch can act complementary to existing techniques. It doesn't have to be that if an AS is reported is a false positive, as you say, we do not suggest, yeah, let's take it down, let's take down this AS. What we do say is that the control plane behavior can potentially expose maliciousness before the data plane. So, and yes, I mean, we will always have to deal with false positives. Think, for example, the reports, where is it? This is a valid report from March 2014, right? And some obviously legitimate ASs were there. So what we're trying to say is that looking at the control plane has obviously some value in identifying those bad ASs before.
Can I ask one other quick question?
Sure.
Do you rely on route views or sort of a global view of routing, or
yes.
could you do this from the observation point of a single AS?
As of now, AS Watch only relies on route views. Thank you.
I had one final question for you. So you mentioned that you were using a binary, you were not using a binary classifier, so you end up with an actual score?
Yeah.
And then did you use a threshold in determining your 90%?
Exactly.
Okay. What was the threshold you used for the score?
I don't have this in my hands as of now, but that really depends. Again, it goes to what is the ground truth that we are training the classifier. If we have a larger set of confirmed cases, then that will be different. So,
thank you.
Thanks.
Thank you, Maria. That was very interesting work, especially in the context of, since it periodically does come up on the NANOG lists, the very important and very tricky issue of how do you do takedowns, and whether you should do them at all and what the damage is. So thank you very much. Next up will be Sean. Sean will be presenting some work he's been doing on NetAssay, which is a flow filtering technique he's been working on.
All right, I'm also one of the Georgia Tech people. Can you hear me? Okay. Let's see. So I work in SDN, and right now flow filtering is pretty terrible. You can only filter based on IP header space, MAC addresses, usual network headers. And wouldn't it be nice to be able to make something like this happen? Bill separately for streaming video. Say have video plans that are along these lines. You have unlimited streaming of video, but 100 gig of something else, or vice versa. Like, can you do that right now? Not easily. Similarly, if you have a foreign AS, like neighbor ASs, you can filter very easily. Say you don't trust a foreign AS, like what Maria was talking about, and you want to throw that through an IDS. Can you do that right now easily? If their address space is changing regularly, it's a little tricky to do. Similarly, can you track a single user and capture all their data in real time? Is there any way to do this right now? Not that I've been able to find. That's easy. People move. They change machines that they're working on. They change access points. Like, I'll use half a dozen access points, no problem, in any given day. So what I am focusing on is a system called NetAssay, and it allows you to monitor intentionally. So there was an intentional naming system developed by MIT back in the late 90s. And the canonical example that they use is, I want to print this document to the closest printer. I don't know its IP address. I don't know what it's called. I know nothing about it other than it's the closest printer. I want to be able to print to that. So I am trying to do something similar. I want to be able to filter all traffic from example.com. I want to count the amount of traffic from gray-listed ASes. Like, is there a spike in traffic happening from various ASes that are known to be not good? And I want to, watch the spy that's in the company. Yes, I know they're there, but what are they doing? Are they trying to export information? So how do you actually go about doing this? Like I said before, switches can understand layer 2, 3, and 4 headers pretty easily. So we have to map the principles, which are the network, the higher level network principles. So the addresses, the names of the usernames of people, things like that. Be able to map those to something that switches can understand. So this is actually pretty intuitive. So I'm going to go through a couple of examples. So mapping a domain. Example.com has a couple of servers. They have IP addresses. Those IP addresses are pretty well known. So mapping is reasonably straightforward. Similarly, ASes, same sort of thing. You can map them to well-known prefixes. And users can either be on systems that have like pre-assigned IP addresses. They could register MAC addresses for like mobile devices that they're bringing into a network. This is not terribly difficult, but things change. Everything changes all the time. Principles, like James Bond, is a static thing. However, where he's going to be, what addresses he's using, that changes fairly regularly. BGP routes change, as everybody knows, hundreds of times a day for simpler networks. And users move all the time. So mapping a change, going back to the domain example, is not terribly difficult. They add a new server. So the change to the mapping is just add a new address. Nothing out of the ordinary. But being able to map this is a little bit tricky to keep that mapping, maintain that mapping. But we have systems that do this already for us. BGP maps ASes to prefixes. DNS maps domains to IP addresses. And they keep these up to date in real time. So we need to exploit these to maintain and perform mappings. So these mappings, all these protocols that I'm talking about are on the network already. So you can, with DNS, for example, that's the easiest one to go with. You can tap into a server. You own the DNS server, you tap into the server, and you can get its database. You can find out when things are being updated, how they're being updated, what IP addresses belong to whatever domain you're talking about. If you don't maintain a DNS database, for instance, you can sniff the traffic. You listen for all DNS responses, you take that, you use that for your mapping. So this, okay. So in order for this to be useful, other than just domains and autonomous systems, which is all that I can handle right now, you need to be able to extend this so that you can add either new protocols, like 802.1x, say you wanted to map users, adding 802.1x is useful. Or you could implement things differently. For domains right now, all that the domain mapping engine that I'm using right now only listens to DNS responses. So you could have it go out, actively query. I want to know from 8.8.8.8, how do I get to such and such an address? How do you get to such and such an address? Because it could be different depending on where you are on the internet. and people use different DNS resolvers. And you can incorporate other data sources. So say you're trying to map users, you can incorporate an 802.1x server, or you can incorporate a Radius server, depending on how you have your network set up. And this allows for users, network operators, to write their network-specific things. I don't know how people have their network set up, and you do. So how do you map certain higher-level constructs that you can refer to by name into something that is addressable by a switch? Unfortunately, there are quite a few challenges associated with this. The implementation right now is rather naive. If it sees a rule, it will install it, which is a problem because, for instance, scalability it's just shot. If you go to google.com right now and are tracing on Wireshark and watching the DNS response come back, you're going to get 7 addresses. In order to map google.com, you'd have to have 7 rules going in the inbound direction, 7 rules going in the outbound direction. Having 14 rules for one domain will explode your rule table quite quickly. People are used to that when it comes to ASes and the 512 rules, 512K rules that we've been seeing lately. Similar problems, but since the rule tables and switches are much, much smaller, you go over quite quickly. Additionally, it's not generalized right now. It is very, very specific to the implementation. And that needs to be changed so that operators can easily write new rule sets. Yeah, and DNS shouldn't have to be handled differently than 802.1x is the easy way to state that. So there are some possible solutions, like less than naive rule installation. Don't install everything. Don't install duplicates. Is there a way that you only can install 2 rules rather than the 14 from the Google example? Is that possible? I would suggest yes, but I don't know yet. You can cache compiled rule sets as well. So from you, I have a couple of questions. What use cases make sense in various types of networks? Like I see various types of network operators here, and I don't know what kind of rules are appropriate for each type of network. And how often do things change in your network? How often are your BGP rules changing? How often are the BGP rules that you may be interested in monitoring, how often do those change? Similarly, what type of, I'm looking for data on those changes. Is it like frequencies and things like that? If somebody has that, that would be fabulous to have, because then I can focus on that particular type of change. And is there interest in usage? A system like this may be of use to some people, it may not be of use to others. Like what do you see as being useful with a system like this? And contact information if anybody wants to get in touch. And any questions? Okay.
Doug Montgomery again. So I sort of missed something very fundamental.
Yes.
Is map to what? I assume a tag that an SDN filter can, pattern match can find.
Okay, so let me head back to one of the just the easy examples.
That's a good question. I missed that too.
Okay. Okay, so in the case for domains, I want to map example.com, that string, that domain, to the set of IP addresses that I can use as a filter. So I want to look for any flows that are coming to or going from those 3 addresses right there. Does that make more sense? So like I can install lower level rules that the switches can understand, match on source port or source IP is that, destination IP is the first one, second one, third one, that sort of thing.
Okay. Seems like all of this would get pretty complex with CDNs and other things.
You got that right, yeah. This is the problem, right. That's one of the other problems. Like, can you map like all your Netflix traffic. How do you do that? Because you got your Netflix.com, that's pretty easy, but all their things are hosted in CDNs. I don't know how to do that right now. So that is one of the big challenges.
And the last question is, do you sort of limit yourself to wanting to be able to do this at the edge? Because if you could find it at the edge, you could map it to some other tag, bury some other.
Oh, change the IP address to something nicer and easier to
I wasn't
filter
thinking
on?
of that. You know, embed something else that an SDN filter could find. That if I could find it at the edge, right? Because
Yep.
some of this gets easier at the edge, right? If I
Do your
just want
mapping there.
the traffic that's coming from a given AS, that interdomain traffic, and I'm sitting on the link, the physical link that goes to that AS, I've got it nailed. It's by port, right?
Yep.
I find it. I put a different tag on it.
Mm-hmm.
That's a much harder problem inside the network than at the edge, right? So
Correct.
So are you limiting yourself to trying to find it at the edge because you could sort of change the problem, map it to some other tag inside the net?
I had not thought of it that way. That way would be one way to do it. As of right now, that is not how I was doing it. I was not limiting to where it could be done. It could be done at the edge. You could match on, bad AS 1, 2, 3, 4. You could match on that, change some parameter, and then within the network, filter based on that easier to understand parameter. That is possible right now.
Any other questions? Thank you, Sean. We can talk offline, but there's quite a lot of interest in the space that you're working in, including some commercial companies that are trying to tackle this very challenging problem. So, great. Thank you. Next up will be Hyojo Kim. He will be describing some of the work he's been doing in verifiable dynamic controllers, putting SDN to some use. He's got one.
Okay. Hello, everyone. My name is Jun Kim, and I'm going to present a part of my work called Kinetic, which is a language and a platform which helps to automatically do configuring changes on your network in face of arbitrary events. So let's start with an example. We sat down with the network operators in Troyak and asked them, it was a security team, and asked them, how do you react to security instance? And we learned that actually, in a very high level, how they do this. So we will have an IDS box up there, and an intrusion is detected. What they do is eventually they will call a lot of scripts which will install rules in their firewalls across the campus. There's a lot of multiple scripts, not because there are multiple firewalls, but also because there are a lot of vendors, multiple vendors, and multiple models. So that's why they have a lot of scripts. This gets worse because you're not just don't have IDS. We also have botnet detector and maybe other build boxes maybe, which will also, if botnet activity is detected, they'll run their own scripts, which will also install or remove firewall rules. And we asked oh, that sounds really complex and is it hard to manage? And yes, it was. They said it's like sometimes a script will call another script and another script, and with dominoes. They said some scripts have custom timeout mechanism in them. And it turns out they have lots of homebrewed, customized scripts are used to do these stuff. So network configuration is hard. Everyone knows this, right? It's because there's a lot of network-wide tasks which will cause the change in the network, which makes it very dynamic. And how to deal with the dynamic, you have to reconfigure the network, but operators kind of rely on these ad hoc homebrew scripts. So because this is hard to manage. And these high-level tasks are realized through a low-level commands, because that is hard to understand. And when they're making all these changes, no changes are actually checked for correctness, so it is error-prone. So we actually did a small survey, well, actually not a small survey, but a survey with network operators, and 20% said they make changes more than once a day. 89% said they're never completely certain that the changes will actually not introduce a new bug. 82% said are concerned that the changes they actually make is going to actually break existing functionality. Of course, yeah? So we were thinking, is there a better way? So in search for a better, we had this idea. What if there's one software program which embeds all the event and reaction relations in it? If you see this figure, you'll have this control plane, which has the software program. And say all the external events is coming to this program. And then there will be a policy update. And finally, there will be rule updates to the switches. Wouldn't this be better? So we actually explored in this direction. We thought about there's some potential benefits of doing this. Because you have one program to configure and manage, it could be easier to track and manage. Because you have a more structured way to deal with all these, to writing policies in face of all these network events, it could be easier to write, read, and understand it. It'll be much better if you had a standardized protocol to and from the switches, whether it could be OpenFlow or a combination of netconf or Yang. So we worked on design and implementation of a system called Kinetic, which is a platform to write a program that will actually automatically make changes to network based on events. We have to use a domain-specific language, which is embedded in Python. And it also has this functionality where you can actually verify what you wrote, the program is actually correctly embedding the event and reaction relationship. So I'll just start with a really simple example we had, the IDS. If you think about it, the initial policy, which should be allow packet, and an infected event happened and it became true, it should just drop the packet. If a new event comes in saying, oh, it's now clean, you should allow the packet. It's as simple as that. And you can see it's actually very easy to actually write this down and illustrate as a finite state machine. So how to encode this IDS policy in Kinetic and make a program, actually, is you actually define what's going to be the event, what's going to be a policy, and their initial values. So the event is infected, and the initial policy should be a allow packet. And you just have to write in the program, define the reactions to these events. If infected becomes true, block the packet. If infected becomes false, allow the packet. So Kinetic actually provides the classes, methods, data types, and data structures, and the guidance to actually write this program. I'm not going to go into giving you examples of the actual code and stuff because that's boring. Just I'm going to show you some examples of what actually we made. So the IDS is just like, as I explained, we were able to do it effectively in 17 lines of code. I'm just showing you that we're not going to ask you to write like 100,000s of code to do this. We also had a program called Data Usage-Based Rate Limiter, which is going to actually change the rate limiting of the user traffic based on the data usage within 24 hours. This was done within about 31 lines of code. We also have a serial load balancer program, which will change the number of servers you can actually redirect packets based on the load. So if the load is booming, you can actually increase the number of servers you can actually redirect the traffic. So these are kind of the things we are trying to automate. But if you think about it, there's only just not one network task you have to realize and automate, right? So you can have multiple of them. So, and Kinetic also provides you to do this in a very clean way. You can combine multiple modules, like you can actually say, for example, maybe you have an authentication model, but two of them. One is through the web, and one is through 802.168. And you actually run it. And if you want to say, like, if either going to allow the packet through successful authentication, you want to allow the packet. I can actually combine modules like this in Kinetic. And say, also then sequentially feed it to the IDS module, and then eventually to the user-based rate limiter. And if you do this, the output will be based on what's the state of each module. Of course, the output will be different based on the dynamic events coming into each module, right? So how you will deploy this? So in Kinetic, as I showed in the earlier slides, you just have this control plane and controller, and you just install this program combined. And the event will just all come to this, and policy update, and rule update. More on deploying. Because it's an SDN solution, we require to have a central controller, and also it uses OpenFlow to pitch rules right now to switches, so it uses OpenFlow. And you can ask, are you asking to change my whole network to use this? Like, I have like legacy switches. Are you asking to make it all OpenFlow compatible? The answer is no. Actually, if you actually be smart and choose the right places to install these OpenFlow switches, and you want automation, you can actually make a huge difference. One of the other cool things about Kinetic is it allows you to verify correctness of the program you wrote. So I'm just going to give you examples. It's possible that you wrote a program, you're not sure whether you wrote it right. You can actually, what Kinetic does, it will automatically translate your program to a model, which will be feed it into a model checker. This is all automatic. So what things you can check is the event and reaction. For example, if it says if your host is infected, which is an event or condition, the subsequent pass is going to be dropped, which is a policy. Another could be if a host uses too much traffic, our subsequent pass is sent through the rate limiter policy. More complex, you can say if a host has authenticated successfully, not infected, and the data usage was under the threshold, our pack is allowed without a rate limit policy. So you can actually check all these things on your program before you actually deploy your program. So we actually need more help. I actually want to ask, we actually want more realistic policy examples, even though I gave you some. What kind of dynamics, like operators, do you have in your campus or enterprise or any network? And how do you implement it? And what tools do you use? I also want feedback. Will Kinetic actually, do you think it will actually simplify your configuration methods in your network? And how does Kinetic compare to your existing tools? So actually, I tried to figure this out during this event, and I went to the sessions of best current operational practices, but I think I couldn't get much of how this is actually done, whether you guys already nailed it, like, kid, you're doing something, is this already done, or something like that. So it'll be really good to get some feedback. This is meaningful around, so. Thank you. We actually have a webpage if you want to actually test it out and see what's more about the project. This open source project, so we have a GitHub repository. And that's my name and contact. And thank you. I'll take your questions.
Do we have any takers on giving him some feedback? Excellent.
Dan McGray and Hopkins APL. Okay, so I'll be nice because I don't want to step on useful enthusiasm, which is always a good thing. Okay. You know, I would just suggest that you look a little bit at how commercial IPSs like Tipping Point and Palo Alto, how they actually work. And by the way, most people actually use IPSs rather than IDSs. Georgia Tech might use IDSs because they feel like a lot of roll their own, but most of the rest of the world doesn't really want to do that. Distributed firewall type stuff. There was an interesting article that I'll forward to you. It was entitled "Distributed Firewalls: How Badly Do You Want to Fail?" And it has a number of different issues that I won't go into here about what all the problems are with distributed firewalls. Cisco is busy promoting a distributed firewall scheme of their own right now, and it's subject to a lot of the same things. A lot of the issues come down to where are you getting your signature feed from, and how that kind of works. And by the way, most IPSs, because of latency problems, actually have to let the packets through initially while they're doing the lookup. Otherwise, you're going to clobber the data stream until you're sure whether it's good or bad, whether it actually looks like an attack signature or not. And they're not fast enough to do that real time. So they have to let the initial kind of packets through while they do the assessment of that, how much latency, the IPS is actually going to introduce into the process. There's a lot of issues in there of how people actually run these kinds of things. Of making ones that are kind of commercially viable, and that's a lot of these companies' secret sauce. That's why they're so expensive, right? Is because they have to, make sure that there's something that you can really put in a production network that's, not going to not false positive, not miss all the critical things that are busy, you know, attacking you, et cetera. So, I mean, you know, I think it's a good effort, and I think I commend you for it that way, but there's just, you know, just take a look at how I don't know how much of the commercial stuff you looked at, but, you know, and how much you can get those guys to tell you what their secret sauce is. But, you know, I would just recommend that.
Sure. But one thing is, like, mostly you mentioned security stuff. But the thing is, maybe this is went wrong, but I think security was my example. And I'm sure, like, in security and IDS and IPS, they actually did a real job, because they don't want operators to, like, manually react, because, you know, that's why you use IPS, right? To actually automatically do that. Is there also another, if you think of load balancing or other rate limiting stuff, is there also commercial things which will make you do that easier?
Yeah, sure. I mean, you know, F5 would like to get into this. But I mean, most enterprises acknowledge that they don't really have the expertise to run IDS, IPS, and simply prefer to buy that as an appliance from somebody who does have the expertise, and they shell out a great deal of money for that. And what you're really paying for is essentially, you know, somebody who really knows what the heck they're doing, you know, actually, you know, making sure that the attack signatures are valid and stuff gets stepped on, right? Yeah.
Right. So you know, you've taken one problem and sort of translated it into someone who now needs expertise in Kinetic in order to be able to implement some of the things they wanted to do.
Mm.
And, go ahead.
Brad Passwaters. So my experience is the first part of the problem set you solved is correct. Basically, you took a set of scripts that were probably written in disparate languages based on what the network engineer liked, and were some of them years old, and nobody knew how they worked, and they were kind of magic. And you combined them to a common system, and whether that common system is Kinetics or Trigger or something else, that is a good thing. That's provable from several places I've worked. When you get everybody working in the same language with the same infrastructure, you get reusable code and things get better.
Yes.
So from that perspective, I think you're probably dead on.
Okay.
The thing where a lot of the problems actually come in, which you didn't talk about, is it's not just making the change and typing the things that are right, but the validation. So if you're going to deploy something over 1,000 switches, 5 of them are going to reboot while you do it for no apparent reason, which has nothing to do with you. So unless your Kinetics verifies that those 5 took the changes or not, you kind of have some of the same problems.
Yes.
And if you're not going back and checking, hey, this switch was processing 10,000 packets a minute ago, and now it's processing 2, maybe I didn't do exactly what I thought. So the bigger picture stuff is what you need to focus on for your next step, which is actually validating the complexity of the changes which you're making. And that's more important with a system like this, because automation allows you to break everything really, really fast.
Yeah, this is no problem. So actually, I think I also heard some incidents in Jura Tech where, you know, suddenly firewalls die because they're suddenly so much. And I was looking at the memory, and sometimes it's hitting something. And because of that, it dies. And I understand. And this is actually a known problem in academia, too. Like, do you want to actually make sure? So Kinetic will verify you wrote the right program, but it's not going to verify you're going to actually install the right ones and in a scalable way. And there are some work on this, on the more data plane stuff, where you actually do an incremental update, or actually there's papers about consistent update, because while you're pushing it, there's also a process of doing this. There's no locking, and there can be some wacky behavior. So yeah, this is actually considered, and we are thinking about combining some of the ideas into Kinetic. Thank you.
Oh, just a small comment that if I understood your survey correctly, you should ask the 11% of the people who were damn sure exactly what their scripts will do every time they push them.
Yeah, maybe I should say, like, if you said yes, why do you think it's yes? Yes. Thank you.
Last up is going to be Nithin Michael from Cornell, and he will be talking about some interesting work he's been doing with high-frequency adaptive routing.
All right. Good afternoon, and thank you for being here for the last talk. I know most people are tired by this time of the day. My name is Nitin Michael. I will be talking about the work that I did for my PhD dissertation. I know it's a mouthful, high-frequency adaptive routing optimization. I'll try my best to get it across in easy-to-understand terms. By the way, just a disclaimer, unlike many people here, I don't come from the system side of things. My PhD was very close to applied mathematics, if anything. The problem I solved is an optimization problem, and I'm talking about implementation results. So there isn't a single equation in the slides, and what I'm going to try and do is get across to you what I did through the results themselves. So please be patient. There might be some logical gaps which I'll tide over as I explain. All right, so where I started my work was this idea that today most networks, at least for their interior routing, IGP policies use shortest path routing. And it's been well known for a while that shortest path routing is inefficient, and there can be problems because of that. The typical example or the analogy like I used to explain this is rush hour traffic, if you will, right, where everybody has some idea about how they're going to get home, and most people's idea of the shortest path includes a few common roads, right? I-95 or I-76, everybody piles onto the same road. And so what is usually the shortest path is no longer the lowest latency path, which is what we're mostly interested in. And the reason that networks have been doing all right and continue to do well, and I've been talking to operators over the last couple of days and learning this and confirming this opinion that I had heard, which is that most link utilizations are maintained at around 50% or lower, just to account for the fact that you could get random spikes that you may not be equipped to deal with. So I thought this was a little bit inefficient when I first found out about this. I mean, you don't see the government building 24-lane highways just because of rush hour, right? I mean, a better solution would be to open up Google Maps, look at Waze, and see which roads are red and go through the green ones, And so if the network has the capacity to absorb the traffic, why doesn't it? This was kind of the question I started with. All right, so just a quick overview of the different techniques I found. Shortest path routing is something that we did discuss, and it has its drawbacks, but it's also widely deployed for a reason. It uses these appealing, it has these appealing properties like its link state, which compared to BGP, say, or distance vector protocols in general, which take longer to converge, link state algorithms always converge faster, and that's a nice property to have. It uses hop-by-hop forwarding. It keeps our routing tables small, instead of having very large tables, and that's good too. But again, it results in unbalanced traffic. We are engineers, right? I mean, for the most part, so the solutions like MPLS-TE, where the idea is, well, I have some idea what my traffic looks like. I'm going to develop some statistical model for what my traffic looks like, and I'm going to pre-program or pre-calculate routes, which will help me, manage my traffic patterns better. The downside is, of course, as the traffic shifts, which it always shifts, you're behind the ball, the routes, the pre-programmed tunnels, if you will, become less useful and performance degrades. Okay, and finally, there is the new paradigm that everybody's excited about, or at least a lot of people seem to be excited about, which is software-defined networking. What I'm going to talk about is not necessarily software-defined networking. I'm going to talk about software-defined networking from the perspective of how it is useful for implementing the type of work that I did. Okay. And not because the type of work that I did cannot be implemented in hardware on an ASIC. It's just easier for us to not do that and just write a software module that works with a router. So the idea with software-defined networking is, well known. You want to shift control from you want to separate the control plane and the data plane. Some people think of this as centralized control, but that's not really part of the definition. It's just splitting control plane from the data plane. And it provides a framework essentially to interface with the data network, right? And a way that you could deal with the problem I mentioned in the software-defined networking paradigm is to gather the traffic, solve this optimization problem that you want to solve. Computers are good at this kind of thing, and write the rules that you found as to how the routers should break up traffic, and you would get a solution. The problem is that now you get into scalability issues, right? And control loop timing issues and other such things, which at least we found to be quite relevant when we implemented this. Okay, so what are some recurring challenges in routing? There is the well-known one of handling elephant flows and mice flows. For those of you who may not be familiar, which is probably nobody, but elephant flows are throughput intensive. They are like things like index copies that Google might run, right? And mice flows are latency sensitive, but not as heavily throughput intensive. And what happens with these elephant flows and mice flows is mice flows can get blocked behind elephant flows, and this leads to degraded user experience. So, and way to deal with this is to find a better way to route these things. And my experience with networks is ultimately I feel it should always come back to routing, because networks should do nothing more than get data from point A to point B in some sense, and I feel it should come down to routing on some level. And large-scale flow placement is another problem where, like I said, you have these optimization problems, but they are computationally expensive to solve. So there is no point in solving them, because by the time you get the answer, you're 2 days behind when you needed the answer. And so that's not something you would necessarily like either. And finally, there is probably the most relevant one, which is adapting to network failures. Links fail, ports fail, there are brownouts, blackouts, routers fail, and you want a solution that would adapt to these in real time. So I sat down and drew up a routing wish list. I said, I was very ambitious. I said I wanted to be optimal. And what do I mean by optimal? I mean that mathematically you should not be able to do any better. If you decide that my metric is I want to minimize maximum link utilization, or you decide my metric is I want to minimize the overall latency in the network, I wanted to come up with an algorithm that you cannot beat mathematically speaking, at least. I wanted it to be computationally light, right? I mean, there was no point in solving these monolithic optimization problems because they were too slow. I wanted it to be something that you could literally get a router to run if you wanted to, right? I mean, it should not be more complicated than, or you'll find when I explain what I did that the bottleneck is really running Dijkstra at a router, right? I mean, that's the most computationally expensive part of the process. It should be adaptive, which is, it should not need to know what the traffic is, because the moment I start saying I want to know what the traffic is, I feel like I'm already behind the ball. So I asked a counterintuitive question. I said, it's hard for me to know what the traffic is in any real network. So what if I get rid of that? What if I don't need to know the traffic and I can still solve the problem optimally, right? Sounds like magic. But it turns out it isn't. And again, here I can use an analogy with road traffic, right? Where when we're driving home, we don't need to know where everybody else is going. We just need to know which the crowded roads are, and as long as everybody in some way is rational about, or super rational really, if you want to use the right term, about which roads to use, then you won't have, I say super rational because if you're rational, you get things like route oscillations, where everybody will shift from the highway to the back roads, and then the back roads are very crowded, and then everybody will shift back to the highway. But if you're super rational, you think, okay, some guys are going to use the back roads, and some guys are going to use the highways, and it'll all work out. So I think the correct economics term is super rationality. And if you're super rational, you don't need to know where everybody else is going. You don't need to know the traffic. All you really need to know is how crowded the roads are, and that is sufficient. And that's the same idea that I wanted to apply to the network. I said, if I know link utilization and nothing else, is that enough information for me? And turns out it is. Okay, so again, I was not constrained by anything. One of the wonderful things about doing a PhD in the theoretical side of things, I just went back to first principles, right? And I started playing with just like 2-node networks and 3-node networks to try and derive the equations. Again, I'm not going to go into the equations, the dynamic equations that govern the splits at the routers. I'm just going to try and get it through to you with the actual tests that we did. So the solution is called Halo. I call it Halo because it's hop by hop, which is nice. It retains one of the nice properties I wanted to have. It's adaptive. It does not require the traffic as an explicit input. It uses link states, which is again essential really because I need to know the link utilization to have any idea what's going on in the network. Also nice because people like using link states. And it's optimal. Optimal is, you're the network operator, you want to minimize something in your network, say it's the dollar amount or the delay or whatever, it will mathematically find the minimum. Okay, so This has some nice properties. So we manage with some of these attributes to get around the issues that I mentioned earlier, which is because it is hop-by-hop adaptive and link state, you no longer have to deal with some of the control loop timing issues that you face with centralized SDN control. Because real-time traffic changes are picked up by using the lower dimensional representation of link utilization, I no longer need to worry about estimating a traffic matrix, which is another sequential approach to this. And the performance results were really surprising. So this is ongoing evaluation. The first thing I did was I went to MATLAB and asked if it works. MATLAB said it works. I mean, first thing I did was I proved a theorem that says it works. Then I went to MATLAB and asked if it works, and then MATLAB said it works. So then I bought some net FPGA boards. I don't know how many of you are familiar with that. Essentially, they're like little routing cards that Stanford makes, or I think it's Stanford that makes it. Anyway, I got it from Stanford. There are 4 1G ports on the boards, so it's like a router with 4 1G ports, if you will. Yeah, exactly. A switch without a brain. I wrote the brain in a program. And Genie is, there was a talk earlier today about NSF and Genie. We wanted to try and see how this performs in a wide area network. This was extremely painful for me because Genie's reserving resources on Genie can be challenging at best sometimes. But still very useful. Also, I'm not the greatest programmer in the world, so actually writing everything took me a long time. I'm more comfortable with numbers. So the results themselves focus on algorithm adaptivity, and network latency is the metric that I used. Was the metric I was optimizing for. Okay. So numerical evaluation. This was the network, Abelian network, right? We took the Abelian network, and here is where I'm going to try. Here is where I'm going to try and explain how the algorithm works to you, right? Every router has a set of equations running on it, okay? And these equations tell the router how to adapt based on link state feedback the traffic splits through its ports, okay? So here, and so this is an iterative algorithm, right? I mean, it adjusts something, it gets link state feedback, it uses that link state feedback to adjust again, and so on and so forth, and you converge. I know here it looks like convergence takes a long time, but when we move to the physical network, you'll see that that's not really true. So say you're in Indianapolis and you've got traffic going to LA, and we set initially that router to point to Chicago, right? I mean, geographically, this is insane. You should really point towards Kansas City or Atlanta unless there is something extremely strange going on, right? And you can see this is like no intervention from us. We just set that like really crazy traffic forwarding rule and just watched what the router would do at that one router, right? I mean, all the other routers were simultaneously doing the same thing for every destination. And you can see that the split to Chicago is reduced to 0, while it also worked out that traffic should ideally split for the given traffic pattern 60-40 to Kansas City and Atlanta, right? Because it's just the equations solve themselves. And then we checked, okay, well, I mean, this is still MATLAB, it's still numerical. We said, well, what happens if the traffic pattern changes? Because this happens all the time. And every spike you see on this graph is when the traffic pattern changes. So right now, there is a traffic pattern, and the program's trying, or the routers are trying to adjust the traffic distribution to solve for that traffic pattern. But then the traffic changes, right? Because somebody else came online and started a new giant flow. And so you see a spike. Again, it starts adapting and reconverges to the new optimal solution. And this is essentially what this graph is showing. And the y-axis is gap from optimal latency. Okay, so now moving on to a physical test bed. This is the one where we use the net FPGA boards. And basically what we did was we built a cube topology. It turns out that's what you can do if you have 4 ports on your switch. And the switches themselves cost about $1,000-something, and you don't really want to spend too much money. So I built this cube topology, and I had 2 video streams. There was S1 to D1 and S2 to D2. Just from the symmetry of the topology, you would expect that the traffic should split evenly across the 3 available paths. Again, we didn't do anything. We simply gave the dumb switch without a brain, this brain, and waited to see what would happen. It took about a second for it to converge to the solution, right? 1/3, 1/3, 1/3. And so we said, all right, well, let's introduce some time varying, like elephant flows to this, where we said, okay, for the first 60 seconds, we are going to flood the bottom of the plane of this cube. And next 60 seconds, we're going to flood the top of the plane of this cube, and so on and so forth. And what the graphs are showing is how fast you actually can't see because it converged really fast, right? It almost looks like square waves, is how fast the splits adapt to the new solutions. And what happens to the max link utilization, right? Because my max link utilization, I'm sending these giant elephant flows, and it's not like I forget about them, right? I need to route them effectively as well. And what happens is when the flow starts, it spikes, and then it immediately converges to, I don't know, about 40% max link utilization as the routers start splitting the traffic. Now this was a compelling one, I thought, where we had video traffic going, and between 104 to 103 we started sending increasing traffic. We started sending increasing traffic between 104 to 103. The idea being that if we used ECMP, which is kind of static, right? Because we picked these multiple paths, equal cost multiple paths across which we're going to split traffic. But now we change the traffic pattern by introducing a new increasing flow, how that's going to affect the throughput and latency of ECMP. And how Halo behaves, for instance. And what we saw was that, as the traffic increased, right, the latency of ECMP, I mean, the throughput that we could drive with ECMP levels off at some point where the latency starts spiking. And for Halo, it was at about 3 times as large where that point happened. This is not really magic. It's because if there is available bandwidth, we are using it, whereas something else is not able to figure that out and use it dynamically. So I'm running out of time, so I'm going to blow through the Genie section a little bit. I'm only going to be able to do this because for Genie, just to maintain consistency, what we did was we reproduced, well, for this talk, I'll show you an experiment where we reproduced exactly the cube topology that I had mentioned earlier and the results that I got from the cube topology. We also tested for a few other topologies. So you see similar results where when we introduce time varying traffic, of course now you see that it's no longer square waves, right? I mean the splits, you can actually see a gap because this is a wide, we need link states to flow from California to New York, right? I mean it took some time, but really the gap exists not because of that so much as our implementation was not the best in the world. We know the bottlenecks are in our code, not so much in the physics of the problem. But again, you see things like the max link utilization spikes when we introduce the time varying flows, but it drops as the switches learn and adapt. And similarly with Genie, exact same experiment. It's much harder to see on a Genie screen capture than it was to see on the NetFPGA topology that I showed you earlier. Same thing, we drove increasing traffic to see what would happen. ECMP failed earlier. Halo, we were able to drive about, I think it's about 2.5 times as much traffic before latency started spiking for it. So that's the gist of my talk. And the reason I'm here is, especially with Genie and with the NetFPGA, what we had done is we implemented those equations that I had derived as a software module, right? On the NetFPGA board, on the Genie, open virtual switch, and that's what was controlling the routing tables to achieve those splits that we were calculating. This could equally well be implemented in hardware, right? I mean, it's basically what was solved is a math problem, really. And the math problem is one of how do you optimally engineer the traffic in real time without knowing the traffic. And so I think the problem with SDN right now is that we haven't seen, and I don't think it's a problem really because we are still at the early days, in the early days of this movement, if you will. We still need smart algorithms and software to realize its potential. I believe the potential is there, but like many people have been at least telling me over the past couple of days, the killer app hasn't been found. This by no means I don't think this is a killer app. I think this is an example of what a good application can be because instead of building it in hardware, you can do it in software. If you had software-enabled switches, and then you can control the routing table doing that, and that would give you potentially good performance, and that's what I'm here to talk about in the sense that it'll be good if I could get like traffic traces or things like that to run it through our system, see if the performance is real with real traffic traces instead of things that I randomly dream up or things that random scripts dream up with iPerf and video traffic. Thank you very much for listening, and I'd be happy to take any questions.
Questions?
Go first.
Okay. Rüdiger Volk, Deutsche Telekom. Looks to me like you have done traffic balancing interior routing protocol. For the dynamic operation of that in the past, for ISIS and for OSPF, the intermediate states, when the overall network converges, have been ignored, and, well, okay, it has been taken as, well, okay, we will get over the micro loops that forms when the converging network doesn't have consistent state. Have you actually gone the extra mile to figure out what nasty intermediate states might occur in your solution?
Actually, yes, it's something that we've spent almost a year thinking about, you know, you're right. The intermediate states with these link state protocols are nasty is a good way to describe it. And that's somewhere where, you know, implementing in hardware is not so much a great solution as implementing in software, where you could figure out what the yes.
Yeah. Well, okay, I'm kind of confused. You seem to think that the usual implementation of OSPF or ISIS is in hardware. Yes, it's a general purpose processor that's doing it.
Oh, no. I don't think that, okay, I'm sorry. I don't think it is implemented in hardware per se or in an ASIC. I'm just saying in terms of writing these things in. So the title of my talk was High Frequency Adaptive Routing Optimization, right? And by high frequency, I mean I want to advertise. This is something that, you know, like I said, there might be logical gaps in my talk. This is something that scares people when I tell them that I want to do link state updates every 100 milliseconds, right? Okay. So in fact, what we've done is do link state updates every 100 milliseconds in all the tests that I showed you results for. This is something that scares people, but what I found is the real reason that it's scary to have link state updates in every 100 milliseconds is because with present routing protocols and present understanding of transient behavior, it is in fact potentially insane to do this. But that, you know, when you're interested in the problem itself, as opposed to constraining yourself with existing technology, then it is no longer a problem to do link state updates every 100 milliseconds. If you have a routing algorithm that's designed to handle link state updates every 100 milliseconds, that no longer becomes an issue. And which is partially why I feel that, you know, at least some of this would have to be in hardware just to handle that speed of updates. But maybe not. I don't know. I mean, you know, my software implementations aren't that great yet. But even with that crappy implementation, I'm able to get to like 100 millisecond update in the results that I've shown. But the transient, to your point, is important. And the transient, the way that we've been getting around it is we wrote an additional module that checks for bad transient states where these loops happen. And we keep executing the equations till those bad transient states go away and write only those splits into the flow table. Does that answer your question? Okay, that's what we do.
Hi, Steve Powell from Level 3. I would be really, I'm really intrigued by this, and I'd be really interested if there's some way to maybe do a comparison to, let's say, your algorithm and just do an apples-to-apples test versus, let's say, auto bandwidth over RSVP, because that would be, from my perspective, you know, real proof of that you have something, because yeah, it's sort of like the standard, I shouldn't say standard, but that's one potential solution out there. And that would, if you were able to show in an apples-to-apples test that your algorithm is much more efficient, that would be the absolute proof.
Well, I mean, again, please forgive me. I agree with you, and I would love to do that. Of course, being a mathematician, I think the absolute proof is if the epsilons and deltas work out, right? I mean, so
right.
and the truth is the epsilons and deltas did work out in this case. But I do want to, and I'd be happy to talk to you more about how we might be able to design such an experiment that might be convincing to you. So the whole point I'm here is to learn that. And
so you just have to hijack someone's network and put your stuff on.
Well, you know what? I don't think anybody will let me, especially as somebody who has confessed to being more of a math guy, anybody would let me touch their network. But I'm sure you'd be willing to share network traces. I mean, I can run it through a computer, and we can check how it performs, right? We can. That would be safer for both of us, I think.
Sure, I can certainly. I can certainly show you some maps of what how spaghetti like some networks can get. So
yeah.
But
the good thing about this, by the way, is it's topology agnostic, it's traffic agnostic, and at least theoretically all of this works.
And the epsilons add up.
Huh?
And the epsilons add up.
And the epsilons add up, in fact, to 0. So that's why it works, right?
Okay, one more question.
Dan McGrayan, Hopkins APL. Yeah, so living in the Northern Virginia, Washington, Baltimore area, there are times everybody drives with Google Maps, and there are times when all 4 roads are solidly red. And if you see anything that goes green, by the time you've gotten there, it's red too.
Yeah.
Because so if you think...
this is what I was partially
Right.
trying to say about the difference between rationality and super rationality. Human beings are at best
You can't count
rational.
on any of it, because essentially behavior just turns into a random approximation of how fast somebody can implement information or doesn't believe in it or whatever. But I guess the point I kind of wanted to get across was, solving the problem, doing over-provisioning does not cost providers all that much, really. So the fact that you started out with a slide that showed 50 or 70% over utilization and the cost of that. That's actually 2x or 3x is not a significant cost to providers, really. Okay. But he's disagreeing immediately. But anyway, but the problem is that's just sort of the cost of doing business, right? But there are times, in certain cases, where you will have several orders of magnitude more traffic will suddenly land on you, right? The Obama inauguration, the Sports Illustrated swimsuit things, whatever they happen to be, suddenly you'll get like 2 orders of magnitude more traffic, and everybody's network melts down, right? And luckily, we don't get a lot of those events. But, that's just basically luck. And looking at that kind of diversity problem, and what do you do under really serious oversubscription problems like that? And right now, everybody just kind of throws up their hands and say, "Oh God, I guess it melted. That was a bad day. Too bad. There's nothing else we could do." Because nobody's going to put in. What was your analogy? If you're normally filling a 4-lane highway, you're not going to put in a 30-lane highway just for the few cases where that might happen. But how would that kind of mechanism work, right?
Okay, so let me answer the question in 2 parts. The first part is I was trying to give you a temporal overview of my own development in understanding this problem, right? Which somebody told me networks run at this utilization, and I was like, well, that doesn't make any sense, and I started looking into the math. Second part of the question, second part of my answer is that. My understanding has been, and I know that this is a problem where you have these spikes happen, but there are 2. I think what I'm addressing is one aspect of the problem, and you're describing another, which is there are times when capacities or demand spikes happen, and I feel that you oversubscribe right now for those demand spikes, thinking that your routing algorithm should be OSPF. Because if you use shortest path routing and you have a demand spike, sure, you might need to have 70% oversubscription. But if you use something smarter and you have a demand spike, you might only need 20% oversubscription, because that might be enough to absorb it. And that's my answer to the question.
I was talking about cases that have enormous demand spikes that just luckily don't happen that often, right?
But even if it does happen,
that's a problem out there that does not have an answer yet. So if somebody came up with something that was useful to it, people would be very interested, right?
If I may ask, when Obama's inauguration happens, as far as I know, my internet still worked. Of course, I live in Ithaca, New York, where there's nobody there. Cows don't use internet, but maybe one of the speakers did say cows use internet earlier in the general session, but in general, I think the internet does handle, things might slow down a bit, but it's not like the network fails. So if with OSPF the network doesn't fail, with this, the network will do better.
Well, actually, I was actually talking about the case of the initial inauguration where nobody expected it. By the time the second one came around, everybody CDN'd the heck out of the thing. So, and they kind of forecast it. But I'm trying to say there are unpredictable events that come around that do not have solutions. And we're just lucky that there aren't more of those things, right?
Sure.
So, it's an interesting problem.
Go ahead, next question.
Have you looked at like what the scheme would do for packet reordering?
Excellent question.
It seems like a perfect packet jumbler.
It is the perfect packet jumbler. No, okay. So again, let me answer that in two parts. First part is I initially thought, why care about packet reordering? Let me see what will happen. So which is why I used video to test things. Somebody pointed out to me that I should really have used audio. Technically, what I streamed was a symphony orchestra performing video and audio. It was the biggest high-def video I could find. That's why it was a symphony orchestra performing. And even, the graph where I showed you things splitting 3 ways, and that was a symphony orchestra's performance splitting 3 ways. And the video didn't even glitch. It didn't glitch when I send a lot of traffic on the top plane. It didn't glitch when I send a lot of traffic on the bottom plane. It didn't glitch while reordering was happening. And the reason is basically twofold. One is because of buffering, and the second is because people don't give TCP enough credit. And a lot of very smart people have spent a lot of time tuning TCP to the point where it does work very well. B, I'm not going to try and force this worldview on anybody, right? So I think that in most networks there are enough flows that an algorithm like this can determine what the traffic splits are going to be. Like basically, I need 30% of my total traffic going this way, 40 this way, 30 this way. And what we implemented in the Genie use case especially was we did flow packing to achieve those splits. Okay, so we didn't split any flows. And that's the way that you deal with it. If you help me, I'd like to see it happen soon. I don't want to keep doing this forever. So, all right. Thank you so much for, especially I know it's the last talk. Thank you so much for being here.
Thank you, Nitin. That was excellent. I think that brings us to the end of the session. Both the speakers and the audience, I think, have learned quite a lot. So it was a successful session. Thanks, everyone, for coming, and safe travel home.